Alright, so let's continue our discussion of trigonometric identities. Next with this one, which involves the cotangent function, cot of x plus y. Now because cot is there, so there is some condition is needed. Cot is not defined for all real numbers. It is not defined precisely for those real numbers which are integer multiples of pi. Why? Because cot is cos divided by sine, and the denominator sine becomes 0 precisely when the input is an integral multiple of pi. So those things are to be avoided when talking about cot, and that's why before we have the identity, these conditions are there. The inputs here are x, y and x plus y. So all of them, none of them has to be a multiple of pi. With that condition, this is the identity. Cot of x plus y is cot x cot y minus 1 divided by cot y plus cot x. If you want, you can write cot x plus cot y also, because addition is commutative. But this is how the formula comes out when you derive it, starting from this left hand side. This is how the denominator comes out. That's why cot y has been written first. And in fact, in the next formula, which is the formula for cot x minus y, you will realize why we write cot y first. But let us first prove this one. The proof is routine, it's nothing difficult. So we of course start with the left hand side. If you want, you can start with the right hand side also, but this is easier. So this is cosine of x plus y divided by sine of x plus y. We are able to use this formula, and in fact we are able to write cot x plus y because it is defined. And that's also why, because x plus y is not an integer multiple of pi. None of these things is. And now we use our usual addition formulae for sine and cosine. And let us also, because we are going to write the formula, let us recall how we remember this formula. When it comes to cos, the terms are cos and sine. They are not mixed. Also, the sign changes. You have plus here, so in the middle part you will have minus in the expanded formula. But for sine, that's not the case. The terms in the expansion of sine x plus y they are mixed. Sine, cos both appear in both the terms. Also, the sign doesn't change. You have plus here, so you will have plus here. That means that the numerator is cos x cos y. We have plus here, so you will have minus. Sin x sin y. Like terms, but now mixed terms for sin x plus y. Like this, sin x cos y. Sign doesn't change, plus is still plus, cos x sin y. Okay. Now in order to get cot again from this, we have to divide by sign. So in the next step, that's what we do. What we do, we divide both the numerator and denominator by sin x sin y. Minus sin x sin y divided by sin x sin y. Similarly, sin x cos y plus cos x sin y divided by sin x sin y. But there is a question, what is the justification for this? You see, it should always be clear why each step is justified. What backs up the step? Okay, there should be a reason for writing each step. Otherwise, you don't really know what you are doing. And especially when you are dividing by something, the only thing you have to make sure is that what you are dividing by is not 0. Can sin x be 0? No. Because just like x plus y, x is also not an integer multiple of pi. Similarly, sin y is also not 0. And that is why it's okay to divide by sin x sin y. Because they are not 0, so their product is also not 0. And in fact, you should write alongside these steps the thing that you have done at that step. Say here you write within square brackets, I don't have space here, dividing the numerator and denominator by sin x sin y because sin x sin y is not equal to 0. There is no need to write an essay here of about why sin x and sin y are both non-zero, but that's clear from what is given. But at least you write something. From an examination point of view, of course, if you are doing something for yourself and you know what you are doing, there is no need to write everything in details. But if you are writing an exam, then it shows that you haven't copied this step from anywhere. You know what you are doing. All right. So now if you simplify things, simplify means these sin x sin y will come under each term. So cos x divided by sin x will be cot x times cos y divided by sin y is cot y, minus we have the same thing here, so 1. Sin x cancel out. Cos y divided by sin y is cot y. See, the y term comes first. Plus, here sin y cancel out and we have cos x divided by sin x, so cot x. So that's how we have our cot x plus y formula. Okay. So the next natural one is of course cot x minus y, because that's how things are going. So that's the next one. Here also, because it's just like this one, conditions are there, restrictions are there. If none of x, y or x minus y is a multiple of pi, then cot x minus y, here however you have to be a little careful. The numerator changes in this way. Cot x cot y we still have, but in place of minus 1 now we have plus 1. The denominator however is slightly not like not how it looks like. I mean, you may think that it should be cot x minus cot y, but it's exactly the opposite. Cot y minus cot x. To have some kind of symmetry between this formula and that one, we write cot y here first, so that it becomes easy to remember both of them. Alright, now there are two ways of proving this one, establishing this identity. One of the ways is just like this. You forget everything. You write cot x minus y as cos x minus y divided by sin x minus y and do similar calculation. Then you will get this one. However, I would discourage that approach. The approach should be to use this one to derive this one, because that's how mathematics progresses. Once you have established something and it can be used to prove something else, then why not use it? But this is precisely what is discouraged in our education system. Say this one comes in your exam, okay. It has some marks, say 5 marks or something. If the mark is really, it has 10 marks, okay, who knows? Then you are supposed to write a long solution. I don't really understand what kind of nonsense this is. If I can prove something very easily, why should I go for a complicated solution? You see the thing here. By forcing the student to derive this formula, just like this one was derived, we are actually making the student dull. We are not really teaching the student how to use an already derived formula to find something new. So I won't really go in that way to derive this one. Instead, I will use this. But whenever you use some fact which has conditions imposed on it, you should make sure first of all that those conditions are satisfied. Otherwise, if you simply just blindly use anything anywhere, you will end up getting something wrong. So what was the condition here? The condition was that both the angles and their sum, none of them is a multiple of pi, an integer multiple of pi. So this is how I am going to start. What are we given? X, y and x minus y, none of them is an integer multiple of pi. Since none of x, y is a multiple of pi. So none of x minus y and x plus minus y is a multiple of pi as well. What we have done here, x of course is simply x, and x minus y we have written slightly differently. There is a reason for that. It's written as x plus minus y. But in place of y I am writing minus y, and I am saying that just like y, minus y is also not an integer multiple of pi. Why? What will happen if say it is an integer multiple of pi? Say minus y is some integer times pi. N is some integer. N may be positive, negative, 0, who knows. But then y is minus n times pi, and just like n, minus n is also an integer, but then y becomes an integer multiple of pi as well, which is not true. It's given that it is not, and that is why minus y is also not an integer multiple of pi. And that's why we can now use the previous identity with x in place of x, minus y in place of y, and x plus minus y in place of x plus y. So, by this condition, these conditions guarantee us that it's okay to use the previous identity. So, by the previous identity, and we also write accordingly, x plus minus y, okay, as if we are using the cot x plus y formula. That's why I wrote x minus y like that. So, you just simply use the previous one, cot x times cot minus y, and we had minus 1 here, okay, divided by cot minus y plus cot x. Okay, now what do you do about this minus y? Actually, minus y will come outside, just like sin minus x is minus sin x, cot minus y is minus cot y. To see y, you go back to the definition of cot. That's it. Cot minus y is cos minus y divided by sin minus y. Cos minus y is cos y, however sin minus y is minus sin y. So ultimately it becomes minus cot y. If you use this, now your expression is going to turn into this. Well, so minus will come outside, so we can start by writing minus cot x cot y minus 1, and here we will have minus cot y plus cot x. And now finally, to bring it to the form that was given, you multiply the numerator and denominator by minus 1. Doing so won't change anything, so we have equality. The numerator now will become this plus 1, and the denominator will become cot y minus cot x. Okay, so that's how you get the formula. At first glance, this way of proving this identity may seem more complicated than the usual dull way, but we have to learn to use already proved results to get new results. Okay, and we also have to learn how we should be careful to first of all verify the requirements of whatever result we are going to apply. Without verifying the requirements, you do not go blindly using results. In fact, that is one source, that is one major source of many wrong things that we end up doing in mathematics. We do not see what conditions are needed first. But anyway, we now have the identity, so we can see what comes next. These examinations and marks, these things are proving to be more harmful, in the sense that if, students need marks. Why would they not need marks, right? Because that's how they are going to be judged, how well you did in an exam. That will be judged by how much marks you obtained. So in order to really get the marks, they get the mentality that we have to write a long solution if more marks are there. And in fact, that's how these things are evaluated also. That is another problem. But that really makes them every time use a long solution. They get a habit of doing that. They do not even stop to think about such ways of getting a quick solution. That should have been rewarded actually. If you get a quick solution which is small but gets the result quickly, actually that should be given more marks. But it's the exact opposite. Alright, so the next set of identities is this. Cos 2x is cos square x minus sin square x, which becomes this as well, and also this. And if x is not an odd multiple of pi over 2, then cos 2x is 1 minus tan square x divided by 1 plus tan square x. You see, in these identities, we have quite a few. There is no restriction on x because only sine and cosine are involved. But in this second part, we need a restriction because now we have tan. So tan means sine divided by cos. That cos should not be 0. That's why we need to avoid these odd multiples of pi over 2. For the proof, we have to again use the addition formula for cosine. We have cos 2x is cos x plus x. So if you use the ordinary sum formula, what are you going to get? Again cos, so like terms, cos x, cos x. You have plus here, so it will change to minus, and then sin x, sin x. And that's how you get cos square x minus sin square x. Okay. Let me just end it here itself. Now, cos square x minus sin square x can also be written as cos square x minus this, and this becomes 2 cos square x minus 1, and simultaneously this is equal to 1 minus sine square x minus sine square x. So 1 minus 2 sine square x. So we have established the first part of these identities. Next, let x be not a real number like this. Okay, x is different from all such real numbers. Then let's start with this expression, 1 minus tan square x divided by 1 plus tan square x. Why did I start with this? I could have started with cos 2x also. I mean, that is also one option. But that's already given in the text. So let us do this one. If you simply write the meaning of tan, it is sine square x divided, because we have tan square, not just tan, 1 plus this. Okay, and there is no danger in writing this because cos x is non-zero because of these conditions. And now it's just a matter of simplification. Minus sine square x, and here we are going to have in the denominator this. What will happen now? This cos square x and cos square x will cancel out. Cos square x plus sine square x is 1, and that means we will be left with cos square x minus sine square x, which is cos 2x. We have just now proved, and that's how we have this one also. Next term, so these are double angle formulas, double angle identities, because cos 2x, the next one is sin 2x, and then tan 2x will also come. So the sin 2x one is like this. Sin 2x is equal to 2 sin x cos x, and if again x is not an odd integer multiple of pi over 2, then sin 2x is equal to 2 tan x divided by 1, is it plus or minus? I forgot. Yeah, it is plus. It's not a problem if you forget any of this formula. I mean, you kind of remember the general shape of the formula. You should at least know what appears in such an expression. But then if you forget plus or minus or little things like that, you can anyway derive the formula very quickly as a rough work. So if what you remembered is wrong, say I wrongly wrote minus 1 here, and then I start seeing what ultimately this thing becomes, I won't get sin 2x. So that will tell me that I have made mistake. So I will then write plus. But anyway, let's now prove this once also. So here we have to use the addition formula for sine x plus x. So when it comes to sine, mixed terms will appear in the expansion. Sin x cos x plus, but both the angles are same, so cos x sin x, and that's how we have 2 sin x cos x. And next we are going to assume this. Next, let x be different from any such number where n is an integer, then let's start here also with the right hand side. 2 tan x divided by 1 plus tan square x. So let's keep the tan x as tan x, and here let's write sin square x divided by cos square x. Well, 1 plus tan square x I think is already secant square x, no? So if you want, you can directly write that instead of doing these things, because well, you can see immediately what you are going to get. Cos square will come here, cos square plus sin square will become 1. So 1 divided by cos square x is secant square x. But if you have memorized the formula that 1 plus tan square x is secant square x, you just write that. Okay, now in the next step, you write tan x as sin x divided by cos x, and the reciprocal of secant square x is cos square x. So after cancellation, you have 2 sin x cos x, which is just sin 2x. We have already proved there. So that's how we have these identities as well. Next comes the identity for tan 2x. Because tan is there in the beginning itself, so we are going to need conditions. If x is not equal to this, and this time x is also not equal to this, where n is an integer, then tan 2x is 2 tan x divided by 1 minus tan square x. So the best way of proving this is to not use sin, cos, those things, but straight away you use the addition formula for tan x plus y. There you take x equal to 5. you understand why x needs to be different from an odd multiple of pi over 2, because tan x is involved. But x also needs to not be an odd multiple of pi over 4. Why? Because otherwise 2x will be an odd multiple of pi over 2, and that will make this undefined. So for this part we need this condition as well. You see, these conditions ensure that x, y and x plus y are all different from any odd multiple of pi over 2, and that is why we can apply tan x plus y formula with x in place of y. So here also, before applying the formula, you should at least see whether the conditions are, whether the requirements are satisfied or not. Yes, they are there. And that's why we do not have to mention those things every time. It's there, you are convinced, so now you can just straight away apply the formula. So applying your usual tan formula, you get tan x plus tan y. In its place now you have tan x itself minus divided by 1 minus tan x tan y. And that's why you ultimately have 2 tan x divided by 1 minus tan square x. Okay, double angle formula for tan. And then comes triple angle formula. So the next one is sin 3x. Because we only have sin, so no need to put any restriction on x, and it will be 3 sin x minus 4 sin cube x. Okay, and in fact there are other formulae also where you can have 4 here, 5 here, 6 here. Those are not explored here in the text, but you have a general formula where there is n. N is any positive integer. Those are quite complicated. We won't need them. So we need till 3. Now let's see how we can prove this. We have, so we are straight away going to use addition formula. We will have to use it 2 times. Sin 3x, and note one more thing, that the end result is in terms of sine, not cos. I mean, not a mixture of sine and cos. Two x plus x. So it will be mixed terms sin 2x cos x. No change of sign because it's sine. No change of plus. Plus stays plus. Plus cos 2x sin x. Okay. Now, what will you do about sin 2x and cos 2x? Sin 2x, of course, is 2 sin x cos x times cos x, plus what about cos 2x? You see, there are a number of identities for cos 2x. But because we need ultimately everything in terms of sine, so we are going to use the sine identity, which is 1 minus 2 sine square x times sine x. Alright. So this now becomes 2 sine x times cos square x plus, we can already multiply this and see what we get. So this will be sin x times 1, that means sin x minus 2 sin square x times sin x is sin cube x. Okay, but now we need to do something about this cos square x. In place of it, you write 1 minus sin square x. So you will have 2 sin x times 1 minus sin square x plus sin x minus 2 sin cube x. So after multiplication, you are going to have 2 sin x minus 2 sin cube x sin square x plus sin x minus 2 sin cube x, and that's why the end result is 2 sin x and 1 sin x become 3 sin x minus 4 sin cube x. Okay, so this is the triple angle formula for sine. Next, a similar one for cos. For cos, however, the cube comes first. 4 cos cube x minus 3 cos x. So let's see this one as well. Proof. Cos 2x plus x. The expansion of cosine has like terms together. Cos, sine, sine. Cos 2x, cos x, and sign changes, plus becomes minus. Minus sin 2x, sin x. And now we will need everything in terms of cos. We do need everything in terms of cos, but okay, so we already have a cos x here. This part, however, we will need to do something. So let's first write in place of cos 2x, its identity involving cosine, 2 cos square x minus 1 times cos x minus. Let's first write what sin 2x is, because for this there is only one expression, which is 2 sin x cos x times sin x. And now after multiplication, we first get 2 cos cube x and then minus cos x and then minus 2 sin square x times cos x. So this is going to be 2 cos cube x minus cos x minus So to turn this into cos, we write 1 minus cos square x. Times cos x. So this will be 2 cos cube x minus cos x. Plus 2 cos x plus 2 cos x. Oh no, we have a minus 1 here. Okay. Yeah, this. That's why I was going to write a plus. Actually, it's minus 2 cos x. Yeah. And now minus times minus becomes plus. 2 of course is there, and cos square x times cos x is cos cube x, and that's how you get 4 cos cube x minus 2 cos x is minus 3 cos x. Okay, so that's how you get the triple angle formula for cosine. And finally does not mean finally for this video. We have the triple angle formula for tangent. If x is not an odd multiple of pi over 2, x is not an odd multiple of pi over 4, and also x is not an odd multiple of pi over 6, where n is an integer, then so many conditions, you will understand why. Then tan 3x is equal to 3 tan x minus tan cube x divided by 1 minus 3 tan square x. Yes. So let us now derive this. I think the best way to derive this formula would be to use the sin 3x and cos 3x formula that we see here. I think that way we will get to it the quickest. Oh, but then this condition seems to be not really needed. Let's see if we need it or not. We have tan 3x equal to sin 3x divided by cos 3x. If x is this, it's given that x is not this, but had x been any such value, 3x would have been an odd multiple of pi over 2. That would make cos 3x 0. But that problem is not present here because of this condition. Alright. Alright, so now what do we write? We write the already derived expressions for sin 3x and cos 3x. Sin 3x is 3 sin x minus 4 sin cube x, and cos 3x is 4 cos cube x minus 3 cos x. Now we would like to divide the numerator and denominator both by cos cube x. And in order to do so, we need cos x to be non-zero, which is guaranteed by this one. We have already used this one, so this won't really be needed. Okay, so I wrongly put it here. It was not there in the text, but for some reason I thought I would need it, but that's not the case. So now because of this condition, cos x is non-zero, and so cos cube x is also non-zero, and that's why I can divide the numerator and denominator by cos cube x. Alright, let's see what we get if we do so. Three sin x minus 4 sin cube x divided by alright. Oh, we do have a 4, but the tan formula doesn't have any 4. So should we divide by 4 instead? Yeah, I think that's what I should do. Not just simply cos cube x, but 4 cos cube x minus 3 cos x divided by 4 cos cube x. This will create some problems though, I think. No, I don't think this approach will immediately give us what we want. I am already seeing some problems, because if we now try to try to simplify the thing, you will have 3 sin x divided by 4 cos cube x. So you have 3 over 4 in this term. And sin x divided by cos cube x, in place of that we can write tan x. But that leaves us with what? 1 over cos square x, which is secant square x. Minus, however, we are in fact getting tan cube x. So this entire thing was done for getting tan cube x. What do we get here? 4. Not even 4, we actually get 1 minus 3 cos x divided by cos cube x is 1 over cos square x. So secant square x. Oh, so in this somewhat very ugly form it's coming. Okay, but there is a way of turning secant square x into tan x, isn't it? What is the identity? The identity is this, right? 1 plus tan square x is equal to secant square x. So in the next step, we are going to use this to turn this secant square x into tan square x, into 1 plus tan square x. So do I have space for that here? I think it would be better if I do it on that side. I don't remember how this is proved in the text. That's why I am taking this route. Let's see if we get what we want. So what do we have to do? 3 over 4 times 10x times 1 plus 10 square x minus 10 cube x divided by 1 minus 3 over 4 times 1 plus 10 square x. Okay, so we are in fact getting everything in terms of 10, but it's a mess. Now let's simplify it. So if we just simply do the multiplication, we get 3 over 4 10x times 1 means this, plus 3 over 4 10x times 10 square x is 10 cube x minus 10 cube x. And what do we have here? 1 minus 3 over 4 minus 3 over 4 10 square x. Okay, so 3 over 4 10x plus 3 over 4 minus 1 is minus 1 over 4. 10 cube x is 10 cube x. Whereas 1 minus 3 over 4 is plus 1 over 4 minus, this one remains the same of course. Yeah, I think now it is coming, yes. Now all you have to do is multiply the numerator and denominator by 4. That itself will give you the formula, because you will then have 3 10x minus 10 cube x, because it's 1 over 4, divided by 1 minus 3 10 square x. Yes. If one wants, I think one can also try to find formula for cot 3x, but those things have not been done in the text. Instead, after this, some other things were explored, like finding out formulas for cos x plus cos y, not cos of x plus y, cos x plus cos y, sin x plus sin y, cos x minus cos y, sin x minus sin y, those things. So that part we are going to do in the next video. So let me just end this video here itself. And that's it for tonight. So see you in the next upload. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.